right? I'm gonna go through the whole paper. There's a part that I'm gonna skip. But you should still give it a read. Like that's my point. Give it a read multiple times. Make sure that you understand a bit. It's like a condense of a lot of what was learned in the last 2 years in deep learning. So it looked like this. This is the research. Like this is everything they've done. There's some part that is still kind of unknown because there's always part like this in research project because they haven't specified everything for multiple reasons. But it all starts with the DeepSeek V3 base model. So this is like the model that was released, I believe, earlier in the year around December 2024, and that model. If you try to understand also like why people were freaking out about this paper, it was not really this paper that were freaking out. Like if you look at all of the other people in the field, like Anthropic, Scale AI, OpenAI, they were freaking out about V3 base, not the R1. R1 is still like the cherry on top because the core thing that they've did effectively is that they reproduced O1 from OpenAI, which was closed source, right? So that's the thing that was a bit interesting. So in this specific scenario, right, we're not doing pre-training, right? Very important to understand. Otherwise, you might get a bit lost about like what the heck they're actually doing, why reinforcement learning is in there. They are doing post-training, only post-training. So DeepSeek V3 base, it's out in the 27th of December 2024. Big model. Also check it out. The optimization that this team has been doing on their mixture of expert and like this particular system is close to insane, right? Very high level of technical knowledge. I would say like it's one of the most frontier labs that are out there, right? So we're not going to go through it, but this model, this big 600 billion parameter model, is the one that is being used as a base to induce reasoning, right? So this whole point of this these pipeline is at the end of this, you have reasoning models, right? Everybody is familiar with like the difference between a reasoning model and just a normal model.
Anyone? Yes, Basir, can you share with us what do you know?
So what I know is that a reasoning model, before doing a task, he's gonna go through a thinking process where he's gonna decorticate the task into like a lot of steps so that he can achieve the task well.
That's perfect. This is exactly it. This was part of kind of a brewing. It's always like this. Like it's never there's one time and then like people invent like this big thing. There was always like the few tweaks that happen, exactly like what happened with ResNet. Like there was always like this little tweak that would happen, and then one lab did the final tweak that made the big advancement. So reasoning model, the thing here is that it's gonna answer kind of prompt itself back and forth, right, before actually doing the final output. That's what's happening. And we didn't know how this was done with O1, right? Before that, you could just ask the model to think step by step, right? And then you can extract, like in a, let's say, XML tag, the response at the end, right? But it was not baked into the model. It was like the model kind of producing it, or like you can loop the model with a evaluator kind of generator kind of workflow. That could work also. But what's happening here is that they are eliciting reasoning on the base model just with reinforcement learning, like just with that. And we knew beforehand that like there was a way to do it with reinforcement learning, but we thought that it would take like a lot of compute to get done. But this thing, the GRPO, so the group relative policy optimization, changed this a bit, and it changed it with like a rule-based reward that are deterministic. So just by, there's no human in the loop here, very cost effective, just by doing the reinforcement learning with this specific type of modelization, you can reduce your compute cost and then have the model being good at code or stuff like that, right? Stuff that are deterministic fully. In order to do, this is for the R1 0, in order to do the R1 completely, it's a bit different. They need to add more compute and they need to have human in the loop for this, because some of the reasoning tasks are kind of subjective, right? But if it's deterministic with GRPO, you can get something pretty solid. And it's the breakthrough reveal here, and this is why reinforcement learning is starting to become more and more important, is because that thing, the reinforcement learning bit that you add on top at the post-training, make the model that was not reasoning before reason, and then the performance increased dramatically, right? There is no inherent change in the number of weight, but the model just got that much better, right? So that's the core overview. How we're gonna run through this, we'll go for first this path. I'll go through the DeepSeek-R1 0 path, right? We're gonna take a look at like this whole chunk. If you understand DeepSeek-R1 0, you understand the whole paper, right? The rest of the stuff is just different method that they've used with supervised fine-tuning in order to make the model more aligned so that they can release it and have it be a bit more useful, right? And they do that with a lot of data. So there's this whole part, this whole chunk that is over here, right? The only purpose of this chunk is to kind of do some data augmentation with a bunch of models, right? That's what they're going for. They have a very intricate and kind of scrappy way of going about it with the least amount of resources possible. They're reusing the model multiple times in order to generate data so that they can then fine-tune itself, so that they can align it with what would a user enjoy conversing with. And then here you have this bit over there, which is like the actual final model that is pretty cool to chat with and like kind of seems to reason like a human would. It's because it was aligned properly. This one reasoned well. It's just that just with reinforcement learning, it's not reasoning for you. It's reasoning for itself, right? So in the latent space, because it's trained with like multiple language and stuff, what will happen is that it can change from Chinese to English to French or whatever, depending on what is most optimal in its latent space to like trigger the right stuff in its thought process, right? So when you're going to look at the reasoning like trace, for you, it doesn't make any sense. And like, it's not formatted well for you to read. Maybe you're going to be compressing the stuff. Maybe it's going to use emojis or characters that doesn't make any sense for you. So it doesn't look that good, but it's performant, right? Versus here, it looked good. And on top of that, they had to align it for Chinese policy preferences, right? When you do that, we're going to see it in a minute. There is some impact on the performance, but at least like the model is now aligned with the Chinese government. And then the last bit that is very interesting is this one, right? And this is why people got very, very excited, because just this is cool, right? But this is still a big model. Like this is still a huge model that you can just interact it with an API. The really cool thing is that they managed to distill the models, right? The Quen and then the Llama's version. And those are open source model commercially that you can use in your app and whatever. But the Quen 32B has high performance in reasoning, which you can host locally on your computer if you have enough RAM, right? It's kind of crazy. So then like people were able to use it and then test it into their application and have literally a reasoning model that they have control over versus just using O1 or O3 with OpenAI. So I know there's a lot of arrows and stuff, but fairly simple. Any question before we start here?
Yes.
Could you please explain a little more about distillation?
Yeah, so the distillation in a nutshell, right, is that you have a big model, right? You have a big model that knows a lot, okay? And you have the input, output, and then you have the weights inside, right? It's already trained. There is some performance. The issue with the big model is that there's a limit about what you can do, and maybe they're not as fast in the inference. Maybe they're not as easy to port, let's say in phones and in like embedded device and stuff like that. So there's a technique that is called distillation. It's not new from this. It's like it's been used for forever. And it basically you have a teacher and a student model. There's many type of this, right? But like the core idea is that you already have trained the big model, and it's like well trained, right? And it has like high performance. And then what you do is you train the smaller one. If you just train the smaller one, it will rarely be able to be as performance as the big model if you have a lot of data, right? There's a limit to the capacity in representing the information that it has, right? Because like the deep neural network are kind of compressing the data into like a hierarchy structure, which then they can query technically. So smaller model have limited emergent abilities, right? But what you can do is train the model with like the in and out, right? But then you pass the data also here in and out, right, in the model, and then you give to this model a view on the weights inside, right? So you're trying to teach the model to, yes, have this correct, but mimic the representation space in this model. So the weight structure and then the information that is in it. So it's kind of constraining where the model will go for the optimization, right? It's kind of like the saying that I know that this space is good, right? Like this is optimal because I have the bigger model. So yes, you're from scratch now, but go more towards here. Versus if there was not this queue, it will maybe go and do a random walk somewhere else in like the cost plane and hit this. It never hit this position, right? So when you're doing this little model is now much better than any model that is of this size because it has a teacher model to help him out. Sometimes it gets very close also to the teacher model performance because there's a lot of waste in these big models, but the representation space that they have is useful and give them enough flexibility to be able to find something that fits, right? I don't know if it helps here, but that's also why you're seeing with OpenAI, all of these models that are like, oh, big advancement, and then it goes down in size and in inference speed. This is what they're doing. They train this mega huge model, and then they're gonna distill it down, right? And then have it like smaller. And now the performance is the same, faster, cheaper, and then they go again, and then there's like this contraction, and then this refraction of the model size. You don't just see it in a large language model. You can see it also like in other type of foundational model. So for example, the whole family of SAM model, so segment anything model, like there was the SAM, they did all of the hard work of doing a SAM. And then like in the same year, they were able to have 100%, like 100x improvement on speed, accuracy, just by like doing very complicated form of distillations. So distillation is a very, very powerful technique. And the cool thing here is that they're doing it this here, and then they're open sourcing the stuff. So it's as if you have the DeepSeek-R1, like reasoning taught in a small model, commercially available, that you can use whatever the heck you want, right? This thing is extremely valuable. So that was a big hit, I would say, for OpenAI business model. Because like this thing, they could literally like have sold it in through an API, and people would have been very, very happy. So that's kind of the idea here. And we're gonna see there's a twist, and there's an important bit in this part. I'll say it right now. When you do this whole pipeline, and you try to do supervised fine tuning on the small model versus distilling the model into the smaller one, right? The performance of the distant model will be much greater in reasoning than the one that went through the supervised fine-tuning step. So this is like a very big breakthrough, right? There was all of these papers that explain a bit that like large language model have like a very large with a lot of parameters have something special, and then there's like an emergent ability that is happening in their latent space. And when you have a big model, and then you're doing this whole flow over here, it's as if, because we haven't added any weight here, it's as if there's a reasoning core inside that you're making pop a lot more, right? And you're saying like this model now need to do reasoning. Like the model here had all the capacity to do reasoning. It's just that it's not like refined to do that. But when you're doing this whole pipeline over there, you're making this core pop a lot more. And if you're trying to do that in a smaller model, it's as if there's no reasoning core, right? The core is not there yet. They haven't found it yet, even if you train it a lot. But when you do the distillation, then it can do it, right? Then like it mimics this reasoning core and is able to do the reasoning. So don't quote me on any of this for that part, but that's how it feels. Like. Okay, so let's start with the DeepSeek V3 base to R10. You'll see there's not that much that is complicated. So this is the paper. You can see over there the performance, and like you can look at everything, right, and dissect all the performance, but it's effectively like a reproduction of O1, right? That's the gist of it, right? It's like to look at O1 over there and the DeepSeek-R1, there's suspiciously very close, right? So you can think about it as a reproduction of O1. And the whole methodology is also not new, right? Their approach, sorry, just here, yeah. Their approach was already highlighted in DeepSeek Math way back, right? And in DeepSeek Math, what happened is that it was like they were trying to do kind of that kind of reasoning step just for mathematical purposes, but this one is much more general, right? So people were already talking about DeepSeek way back because they saw this coming and they didn't understand how they were really using it and doing it. But then they gained steam with DeepSeek V3, and they gained steam again with R1. Yeah, so that's the core idea. We're gonna go to a breakdown of GRPO, right? The group relative policy optimization, but I'm gonna put it into contrasted to PPO, which is the thing that is used, the policy optimization method that is used in the reinforcement learning with human feedback. That is, technically speaking, we think that's what O1 was doing over there. So the interesting part here is that if you look at the prompt they're using, it's just this. There's nothing else, right? It's not a complicated prompt with multiple examples. It's just this. Just with that prompt on DeepSeek V3, they're able to elicit reasoning if they're using like the proper reinforcement learning kind of feedback, right? And then what they're doing here is that there's a reward model in R10 that as you can see it as having multiple branches, but all of the branches are deterministic. There's an accuracy reward, right? So let's say they're doing lead code type of stuff. They're going to go to a compiler, try to run it, right? And then you're going to get some sort of reward to say, let's say it compile, but it doesn't pass all of the test cases. You're going to get some reward that is going to be fed back. But if it passes all the tests, you can get the maximum reward that you can. And then there's some formatting reward that you can also add over here, just to keep the stuff within the think tag, so that like the reasoning stays there, right? So if the reasoning is out, you can get like a mega penalty. If the reasoning stays there, then you get like a good reward. So over time, this is good. And then this is cool because you can extend it however you want, right? There's actually right now an open source version of this whole thing, of the whole methodology from Hugging Face. You can check it out. And then they give you all of the tools that you need in order to like do your proper reward function if you want to. So that's kind of that. And if we look at the core of this, it's only doing reasoning, sorry, the GRPO here. In this pass to create R10, it's not going through the chain of thought language consistency reward still, right? This is for the R1 pass. And this consistency reward that they added, it kind of tanked a bit, like I said before, the performance. Yes, they've released a reasoning course. Greatly recommend it. It's their post training team that was doing the whole reproduction effort. I can show you the code. It's over here. The code is open source. You can take a look at like how they've implemented, let's say, KL divergence and like the whole GRPO algorithm. It's very simple. The algorithm is not complicated. It's just that the fact to think about it and set the structure like this, that was the breakthrough. So if we look here at the GRPO, right, the PPO and then the GRPO are a bit different. Both of them are kind of a reinforcement learning based type of setup. And if you think about reinforcement learning, there's a good video on the proximal policy optimization. This is based on another algorithm, I think TPO that's called. But then this one is the approximation of the other one. And basically you have two networks. You have a policy network and a value network. And that was the algorithm. You needed to train two models at the same time. This is very computationally intensive, right? So you have one network that is, it's about like finding the right value on this grid. And then another one, which is like the weight technically of the network that you want. That is finding like the probability of the moves that you need to do, right? This is for moving into a grid. In this particular case, is to outputting tokens, right? I think Ayub, you had a question?
Yes, I just want to mention that I think in DeepSeek math or the other paper, the R1, they mentioned every like reinforcement learning method, like the PPO, the DPO, the GPO, I think also. So they have mentioned them, and why did they choose the GRPO?
Yeah. It's over here.
Yeah.
I can link to it if you want to. There.
Yeah.
But yeah, the as you see here, the PPO versus the GRPO, the main issue is that there's two models here, right? As you add more model to your training regimen, it becomes a beast. Like you're starting to have a bigger and bigger setup. You need to have more compute, but don't forget, like DeepSeek are kind of constrained in terms of compute. They're doing every optimization possible to get the most juice out of their GPU. They're really doing crazy stuff. So this for them was kind of a out of necessity, where they think like, hey, if we can just remove the value model completely and find a way to get the I'd say the advantage without a value model, we should be good to go, right? We should be all good. And then they are doing it, and then they're constraining it in R10 by not having non-deterministic reward. It's always deterministic reward in the path that we're talking about right now. So what happened is that you're doing like some group computation where you're asking your model to do multiple outputs for like one question, right? It's kind of this classical kind of technique in machine learning, which is called a boosting, right? You have one model or like a multiple model that are going to do like multiple output, and then this voting of this output is what's going to be helping you to iterate on your model. So this is a bit what's happening, right? So they can just pop out completely the value model and use the same model with its multiple output in order to figure out like how it should change its parameters effectively. There's a difference here that is pretty significant in the KL divergence, right? If you look here, the KL divergence has been put back into the policy model in the formula, while here the KL divergence was jammed and literally jammed with the reward function. They did that kind of out of necessity because it would have been a bit complicated to put it in there in the group. So they decided to move it back, and it has a weird form. We can take a look at it if we have some time. But now with the KL divergence here, the formula, if you look at it quickly, it looks atrocious. It's huge, right? But if you walk through it slowly, it's not too bad. So it looks somewhat like this for the PPO, right? So this is the PPO algorithm, right? And then you have multiple loop going for to get to the end result. And basically, it's like an expectation that you're doing, and then you basically like some sort of quote unquote averages. You have 3 blocks. You have this one, right? And then you have this one, and then you have a last one, which is now this one. There's only these 2. The KL divergence is over here, right? So there's 3 blocks to take into consideration. One block is doing like normal reinforcement learning, right? Like it's just using its output token, right? That are scaled in order to figure out if where they're going is better than before. And then the advantage term, which is just a reward, right? That is scaled in a specific fashion, is used to reinforce like a set of output better than before in each of the direction, right? Either you're going to do more of this and less of that. This is a pure reinforcement learning type of setup. The rest of it, the clipping part here, is to avoid restrict the model so that it doesn't go in each direction. If you just do reinforcement learning without some sort of penalty term for changing too much, it will go wild. Like usually it will just diverge in all directions. It's very difficult to keep this model in check, right? So there's 2 ways they're keeping this in check. There's one way, which is the clipping here, where you have an epsilon. And basically what it's saying is that here is the model. You have an epsilon. You can move here and here, right? In each of these directions, but no more than that. If your move that you're trying to do with like the new parameter space that you change for generating the output is like over there, we're gonna clip it here. That's what it's meaning in this clip section, right? So they're taking the minimum of this. So either it's a clip part, or it's this part if, let's say, it's only decide to move over here. This is fine. So we're restricting the movement of this model to a step. The other part is doing the same thing, but at a broader kind of scale on the reference model, which is DeepSeek V3 base. Because remember, we're only doing post-processing here. We don't want the model to change too much. We just want to kind of change a bit this parameter so that the reasoning core pops off a bit more. So to do that, right, you're using KL divergence, and KL divergence is basically the difference between 2 probability distribution. That's all there is, right? And you can think about like the parameter here, the pi is the parameters, as being a probability distribution. So you have a probability distribution for right now, and then you have a probability distribution for DeepSeek V3 base, right? So this is the V3. This is, let's say, our new one, right? If they diverge too much, right, we're going to have a higher penalty over there, which is controlled by the beta coefficient. So if for whatever reason you find something that is very useful but is very different from the DeepSeek V3 base, right, you need to have a high amount of rewards in order to justify moving there, right? If the reward is just like a marginal, and then you're moving in a completely different direction compared to this probability distribution, you will not be able to go there. The penalty will be too high, right? That's what they're trying to do here. So the KL divergence part is very, very important to anchor the model into what was done in the past. We're doing post-training here. We're not trying to change the model completely because we already know that V3 has good performance. What we want is augment this performance with reasoning. So that's not GRPO. This is PPO. The GRPO, if you look, is just a rearrangement of these terms that we've seen. And there is now kind of another average that we're doing based on the groups, right? And the group is like, you have one question, right? And then instead of doing just one output, you're doing multiple output, right? All of this is considered a group. And then if you have multiple output, you're going to have multiple reward over there, right? So then you're going to have multiple advantage over there. And that's kind of how you're going to use these terms. It's the same thing as before, except instead of just having one, right, made by the value network, you have multiple made by the same network. So a bit like of a pseudo boosting type of setup. So don't freak out about that part. It's all good, right? Focus on this part over here. And here it's the same thing. There's just 3 sections, right? There's this section over there, this section that we've seen, same thing, it's clipping, and then this section, which is the KL divergence. It's exactly the same thing. The form of the KL divergence look very different, right? If you take a look at this one, right, this, and then you take a look at like this part over here, it doesn't look anything like it's supposed to be. Like these two are flipped, and then there's 2 of them for some reason with the log, and then the -1. So what they've what they've done, and they explain it over here, is that they're using an unbiased estimator for KL divergence, because you're never actually doing KL divergence ever, because you don't have the time to go exhaustively and calculate the actual probability distribution and all that. So you're always doing like a Monte Carlo estimation, right, on the KL divergence part. But what they're saying is that their KL divergence is better than this one, because this one is actually, I believe, it's unbiased but has high variance. This one is unbiased and has low variance, right? So they're using some trick in order to reduce the variance. We can go over here, but like this trick was written by Schulman, which was, this is a very important researcher. He was the co-founder at OpenAI. He was super important in Anthropic, and now has created his own research lab. I think Thinking Machine, it's called. It's very new. Okay, so that's the idea, and that's pretty much that. The advantage, if you look at it here, they are calculating this way. So you have, it's kind of like what's it? A metric of how good this reward is compared to the group, right? That's kind of what it is. So you have like a normalization that is done here, actually a standardization, if we want to be a bit more precise, taking the mean and standard deviation of the group, and then you kind of normalize that part so that you can add it over here. And this will be used for this reinforcement learning type of setup to decide if you should think about it, if you should put more weight on this or not, right? So this is kind of the thing. This part and then this part, right? Here you have the previous step. Like, so this is what would have been the output with the previous step. This is the output on the current step, right? So you're doing like one divided by the other in order to check how different is this thing, these output compared to the previous step, time the advantage over here. So this is how right you are, and this is how confident you are about like the current output that you're doing. And remember, this is like token output. So there's multiple of them that are being sent out. So that's in a nutshell. If we look at it in a more visual way, right? You have like the prompt. So this is one group, right, over here, and this is another group in another like a run that you're doing, and this is your completion, right? So this is like one output, another output, another output, another output. You have all of these rewards that are getting created, and then you have all of these advantage getting created, and then you're gonna use it with the KL divergence here metric that you're gonna calculate, and you're gonna do this minus that, and then you get the mean of this with the grouping stuff that you're doing, and then you get the objective. So that's kind of how this part looked like. If you look at the pseudocode, it's very simple. And if you look at the actual code implementation, which if you're very into this stuff, never hesitate to pop open the actual code implementation, because there's a lot of things that get demystified directly. It looks very complicated, but in the implementation, it's like 6 lines of code. It's nothing that complicated, right? It's more of like the statistical property and this architecture that makes sense in order for the learning to happen in an efficient and cost-efficient manner. But when you look at the code, there's nothing there much. So here, this is the first initialization of the policy model. This is actually the reference, but in this case, they're saying no. They're saying that the reference is this model, which is in the the various epoch that they're doing over the model. So there's maybe some let's say confusion here about the actual implementation, but I think the reference model is the DeepSeek V3 base. And then you do your step over there, right? You get the old, which is the one from the previous step. So this is what you're using. And then you sample the output from the old, you sample the output from the current one, and then you're going to compute the reward, the advantage, and then you're doing your GRPO stuff on each of the group that you have, and optimizing based on the objective that we saw before. And after that, when you're done here, this is where you're going to update the model. At the end of the whole thing, you're getting this thing, which is the DeepSeek-R1. So I'm not going to go into the code or the KL divergence part. You can take a look at the blog post. It's pretty well explained. Just know that it's they're trying to unbiased, they're trying to keep the estimator unbiased while keeping the variance very low. So if we look at the performance of DeepSeek-R1, the interesting part, this one is interesting because as the step increase, right, the performance increase. Like there's no more let's say weight being added or any sort, right? You're just doing post training, and post training go from like in this benchmark, the IME benchmark, go from like not that great to like better than O1, right? Directly. So this shows that like this is what O1 in post training, this is what happened. And if you look at this this graph, as you're doing these reinforcement learning loop, in its own, the model is learning that it should think more, right? So the reasoning kind of just emerge, because like the GRPO is not like built out to elicit reasoning, right? And if you think about it, the prompt that they've done here is not set up to actively elicit reasoning. The only thing that they have here is like a reward for formatting, right? Remember that? But this doesn't say like think more longer, right? It just says just keep the stuff in the think tag. Same thing for accuracy. It doesn't say like think longer and you're gonna get more reward. So on its own, it realized that as it thinks longer, the reward will be higher, and then the accuracy will be higher. So it's just thinking longer and longer, to the point where at 8,000 step, it's taking for like quite a long time, right? This is also why these models are kind of slow, because the accuracy comes from having these think tag being filled up with like the reasoning steps. So that's the setup, and then like it's this is an interesting tidbit here. The model says in its own reasoning tag, wait, haha, this is an aha moment, I can flag here, and it looked very human. When you test it out, right, R1, people were a bit surprised because it looked like some dude that was thinking about the problem, right? It has a very human-like kind of output. However, if you just look at R10, at some point it speaks in Chinese and switch to English and then think in emojis and whatever. So this is one of the main drawback of R1. So they wanted to make a system where it will align a bit more with what you expect, right? So this is where we're at this point. We've done this loop over there. Any question before I go into the rest of the stuff?
Any questions, guys?
So you could technically stop here, right? And you get it. Like
I think, sorry.
Good
I think
question?
Basir has a question.
I just had a question when we talked earlier about like the deterministic approach of the reward, like is it based on human feedback?
Yeah, so it's not. The R10 is not based on human feedback. The rest of the part will be based on human feedback, because it's kind of subjective what they want the model to be rewarded about, right? So they haven't explicitly showed it with this like a diagram or whatever, but the rest of the part is not really using GRPO directly. In this section here, there's actually another model that is doing the value section. You need that the value model when it's how to say it, a bit ambiguous, right? But with the supervised fine tuning, you can align it and say like, hey, like this is what we like, this is what we want, right? And then the value model will kind of keep that into consideration. So R1 is with that type of setup. I'm not even sure that they're using GRPO. They can't use GRPO here. They're using like PPO, I believe.
I think the question from Basir was in what is the difference between the reward given when using PPO and the reward given when using GRPO, right, Bashir? Because we said that with PPO we have I'm sorry, we have direct rewards, or what did you call them?
Deterministic.
What?
Deterministic reward, yeah.
Deterministic, yeah, I'm sorry. I'm fasting really hard. Deterministic reward, and when we talked about GRPO, it was a different kind of rewards. He wants to understand the difference between these.
Yeah. GRPO, it's deterministic reward. PPO, you can have both. It doesn't matter, right? But like the optimization is that if you have deterministic reward, you don't need PPO. You can just use GRPO because there's no, the reward model here is very simple. It's literally just like how to say it, like getting it out from some system that will tell you if you're doing good or not, right? The difference here in the reward is that the reward is mainly built out and completed with the advantage with this value model. And you need that value model in some cases because it's subjective, right? But you align that value model network in order to align with your preferences as a human. So you do that before, and then after that, you're able to have this do the judgment. So the kind of LLM as a judge type of setup. So that's that. If you want more information about PPO, I highly recommend this. It's like very high quality breakdown. It's not too long of a video, and it goes from like the very basic to the actual PPO algorithm at the end. Okay, perfect. So we're gonna check out here the high-level overview about what's happening. But the cold start in the stuff, what they're trying to do is increase readability in the think tag, right? The chain of thought that is happening, and to just try to have better performance in the subjective type of task. So to do so, they have a bunch of already long chain of thought, right? They're trying to hit that. They're trying to hit this point. Sorry. They're trying to hit this point earlier. They already know that if the chain of thought is longer, right, the performance will be better. So instead of trying to let it for 8,000 steps figure it out itself, let's just give it a hit and say like, just think longer. Like look at these chain of thought. We're gonna supervise, fine tune it, and then this is already better, and it will tend to already be here a lot earlier than the R10. R10 started from scratch here and like learn its way through this point in time. So this is what they're doing with the supervised fine tuning, and then they're adding like this consistency reward, right? And this one is a bit hurtful. It's the consistency reward so that like the thoughts are formatted for you to read, right? And they're saying that like when you do that, it tanks a bit the performance, which is interesting on its own. It's like a reasoning model could be technically even more performant if you can't understand what it's thinking about, right? So that's a bit of some sci-fi stuff. Once you're out of this, right, you're gonna have a base model that is supervised, fine-tuned, and that has been augmented with reinforcement learning. And this model will be used to, I'd say, generate data. That's the whole purpose of this. and it's uses it to generate a bunch of reasoning data so that we can supervise fine-tune the actual model, the base model here, this one, right? So they're training the model and then use it for generation and then throw it in the garbage and then redoing this loop with like the data that they need. If they already had that data, right, the pipeline will be much easier because it's just this step that is R1, right? But since they didn't have that data, they had to generate it. And then they're doing the same thing here with non-reasoning data. So they're also doing non-reasoning data so that like the model is still performant in some of the tasks that doesn't require reasoning. So they're again using DeepSeek V3. They're using chain of thought prompting here to generate a bunch of non-reasoning data in multiple fields. And there's also some undisclosed amount of data that they had for DeepSeek V3 supervised fine-tuning. So in this paper, it's explained a bit more. And then with this, they kind of combine the two and have 800K sample of supervised fine-tuned data, right? At this point in time, they're doing supervised fine-tuning on DeepSeek V3 base, and then doing the reinforcement learning with like different kind of rewards. So here, the reward is a bit different. Here. So the reward is a bit different. So they have a bunch of reward to capture the human preferences here in complex and nuanced scenario. So they haven't disclosed exactly what they're doing, but they have, you see the two reward that we saw before. They just have more now, and it's embedded into also a value model that will help like do the final loop. Here, they are saying something very interesting. For harmlessness, we evaluate the entire response of the model, including both the reasoning process and the summary, right? So the think tag and stuff, and they're trying to kind of, I'd say it like censor some of the stuff that they don't want to see. And then they say that, where is it? There was one part where they're saying in the result, yeah, it's in the result section, that doing that harmlessness and helpfulness type of stuff kind of tank in some of the benchmark, especially the Chinese one, because they're kind of censoring some of sensitive material, let's say. So the I would say the censure that is happening is in the weight, right? So there was like some question about like if the model is nerfed a bit in what it can say in the application that is online, DeepSeek, or the actual model. It's kind of both. It's censor over there and also in the literal weight of the model. There is some company that are trying to uncensor it by redoing supervised fine-tuning in the reverse direction for the part that is has been nerfed a bit. Okay, so if we look at the performance quickly, nothing new here. We saw it at the beginning, but it's doing pretty well over here in English compared to a few models that the OpenAI one, the GPTs, the even DeepSeek V3. It's better than like what it was before. Even Claude, it's doing good at the code, but not as good, let's say, as OpenAI, but still much better if you look here than DeepSeek V3, right? So coding and reasoning kind of go end to end. It's more performant when you have that. And then math, this is perfect. Strangely enough, Chinese, not great. And this is the nerf that I was talking about. It was better before than after, mostly due by the fact that they had to censor it a bit. Okay, so that's this part. And the last element that I want to go through is the distillation. Any question on this section? It's really just a big pipeline to generate data, right? This is what you have to get out of this. Like it's using the model in various ways to generate the information it needs. If you already had this reasoning and non-reasoning data sample, they will not have done any of this. Okay. Lastly, the distillation. They went through the process that I've discussed before, and if you look here, The part that is pretty interesting is these are the model that we're benchmarking against, and all of these distill model, even the 1.5B, they're not too bad. The 32B from Quen is kind of good all across, right? And then the bigger the model, the bigger the performance. But here, the performance of the Llama 70B is, if you think about it, almost 10 times smaller than the DeepSeek V3, and still the performance is kind of good, right? They did the last let's say experiment on the two type of a flow. One flow where they're doing supervised fine tuning on Quen, and another flow where they're just distilling Quen from R1, right? So they're doing the R10 flow on Quen, and then they're doing the distillation from like the DeepSeek R1 onto Quen, right? This is the two difference, and then this is just Quen, like a normal. If you see here, the performance of doing R10 on Quen is not that great. Like it's not doing anything new, right? It kind of is not learning not even learning. The reasoning core is almost not even there, right? It doesn't know what to do. The other one with the distillation, the performance is much bigger in most of the benchmark that we have, right? There's not more weights, right? The weights are the same. It's just learned to kind of mimic the reasoning core of the R1 model. And this, I would say, is one of the most important practical information that you can get out of this paper. It has everything, like the fact that the bigger model have emergent ability, the fact that the smaller one get better with the distillation, the fact that the small one can learn to do reasoning also, that reasoning has some power to it, right, for like the performance, but that the model need to have enough capacity to represent it properly. But that's it. That's pretty much it. And they did a cool thing at the end. They showed everything they tried that didn't work. Very rare to see that level of transparency in an AI company, to be honest.
Exactly. That's what I really liked about the paper, that it showed the different methods used and why they didn't work and why did they choose the right method. It's not like just benchmarking tables and saying, yeah. They really did explain. So any questions, anything Mr. Yacine should clarify? I really need to move. Yes, yes, Bashir.
So I wanted to ask, we said earlier that it's like the LLM during his, or the model during his training had built a core for reasoning, but it just didn't pop up. And like we post-trained it later to like show that core, so that that core pop up, and that he knows how to think. I was wondering if it could be considered like fine tuning, like is it post training or fine tuning, or like I got confused a little bit.
Yeah. This is 100% post training here, right? Like the making this thing pop is like is post training. It's not another step in the pre training setup. Pre training is completely different. It's just that like we're making this thing pop a bit more. If you take a look at, I don't know if you ever read this paper, Tool Former. Right? Anybody read this paper? Okay. Another pretty important one. You can teach the model to use tools, right? Like literally, you can teach it to figure out when it doesn't know, and you need to ask. To like ask a calculator, like what's the square root of this thing, or ask, let's say, weather API, like how much degree there is out there in this city, right? You can teach the model to do that. This is mostly post-training that is happening, right? So it's the same kind of idea. In the core of the model, right, in this representation, it kind of knows what it doesn't know, and to some extent, right? And then you can leverage this fact to make emerge the need to call something external, any tools, and then it understand like what tools they need to call when. This kind of use the same idea as the reasoning, but specifically for tool use. And this is like has been implemented, the tool former methodology, in most of the LLM provider out there. Like when you're using tool use, is because in the post training stuff, it learn how to use a bunch of tools, and you can even make it learn yourself with some of the library out there how to do the tool former. So it's not that complicated, and doesn't also require a lot of data, right, in order to understand what you need to do. So kind of the same idea. The models, the big models, it's very important. We don't actually know how much they know about stuff. There's a lot of emergent ability that we figure out with them by tinkering with them. It's almost like a mini animal that you learn that, like, hey, now it can do that stuff, right? It can use a hammer or whatever. So that post-training setup, I think, will become more and more important in the current years, and you should kind of get accustomed to these type of paper, because it's a bit weird in terms of like traditional machine learning sense. What's happening here? The model is already trained; it can do stuff. Now you're like through supervised fine tuning and like reinforcement learning, like make some facet of the model emerge a bit more in order to have this new ability that you're looking for. Yeah, this is at the cutting edge of what we know right now.
I think is it like the tool former? Is it like function calling fine tuning?
Yeah, it's kind of it. And if you think about it, function calling is just like natural language still, right? It's just like you need to know the input, output, the parameter that you need to pass through, and then you need to know also like where you're gonna pass this in your output. So the model has multiple paths. There's one path where it creates like these API tag, a bit like the top tag that we talked about, and then it decides which parameter you need to put and knows what tools in like its repository of tools you need to use. You take this, and then in a second pass, it will extract the API tag, do the call, wait, get the stuff back, inject it back into the space that you need to, and then you return this output, right? Kind of the same roughly idea, but in this case, we're injecting like thought steps in between, right? And then you get to the result at the end.
Yes. Any other questions, maybe? Yes, Hiba?
So I just want to ask why they didn't use the DeepSeek-R1 for all of it. Like why they decided to incorporate some cold start data from the DeepSeek-R1 into V3 through some supervised fine-tuning before the reinforcement learning.
Yeah, so they didn't at some point they stopped to use DeepSeek-R1 0 because they've added another consistency reward, right? And they did some supervised fine tuning so that the model go faster into like the spot where it's generating longer chain of thought. That's the whole reason, right? So with DeepSeek-R1 0, what they actually saw is that you do the reinforcement learning, and the optimal thing to do at this point is have long chain of thought. So why not just supervise fine tune it to get to that point earlier? At this point, it's not DeepSeek-R1 0, it's something else. It has a long name, like it's like DeepSeek V3 base plus supervised fine tuning plus like reinforcement learning. Like it's this thing. And then they're using that now because it has been fine tuned and reinforcement learned to generate these long chain of thought that are useful to generate literally like long chain of thought and reasoning data, right? That data become the training set for DeepSeek V3 based. That's kind of why they've done that. The purpose of R1 0 is specifically to showcase that like longer chain of thought can be obtained with reinforcement learning.
Yes, exactly. Any other questions? Anything you need to clarify? Well, for me, I think reading the papers will help you guys a lot. So try to read the DeepSeek math first, because the genius, I think, my opinion, the genius comes from DeepSeek math before what we have now, the drama with DeepSeek-R1. Sorry. And yes, you need to understand how they did it, how they thought about changing from PPO to GRPO, and how did it help. I think with Mr. Yacine clarified this uh, in the talk. Well, beside that, if you haven't, I don't know, read the article again, read it and send us the questions. I will make sure to send your questions to Mr. Yacine and
Yes,
get his
please.
feedback.
Yeah, for sure.
Yes. One thing I have is the most fascinating thing for me in the DeepSeek math. It was the way that they collected the data set.
Yeah,
They
yeah.
had
This
yes,
whole machinery is something else. Like the folks at DeepSeek are very, very resourceful, right?
yes, exactly. They have limited resources and they try to take as much as possible from the limited resources they have. So the way they use stuff, and they like they manage to do great things with so little
Yeah,
uh, help.
yeah. It's I think it's going to be one of the lab we're going to hear more and more about, because they have funding, they're cash flow positive with their operations right now, and then they're churning paper out with new novelty in the like the cutting edge again and again. So if there's a lab that you need to follow a bit more closely, I think it's this one, because anyway they're gonna reverse engineer anything that the closed source guys are doing.
Yeah, exactly. I think the engineering genius team is well, is genius. Yeah. So well, if you don't have any questions, we don't need to. Yes, Basir. Yeah.
Maybe as a last question, or I don't know. I just wanted to ask for your maybe experience. I don't know. Like, I find it fascinating how in your videos and stuff you explain the papers so well and understand them. Like, what is it your approach to
Yeah,
understand and read the paper?
it's a very good question. Um, yeah, no matter the fields, right? If you're doing the I don't know, if you're doing biology, if you're doing neuroscience, if you're doing like physics or like machine learning, you have to understand what actually is a research paper like this. Like it's the combined effort, right, of many very smart people at the literal cutting edge of science, right? It's not a book. It's not something that you read from start to finish a novel. It's something else, and this thing is always embedded into the context it was written. So if you're reading like a paper, let's say from Jan LeCun from 30 years ago, I would say 95% of the ideas are not that relevant, right? But like at the time, it was super relevant because it was within the context that it has. So some of the stuff that they're saying are kind of not 100% true, or like if there's a misconception about where to go, but there's a core that is super important. Even in this paper, for sure, there is some of that that you can even highlight. I highlighted a few of them, right? But there's stuff that like you have to be a bit wary about. But the core is there. So the way you need to read these things is you really need to uh, uh, kind of study it in multiple paths, right? You first do a pass in order to understand the context that it's living in, right? And then you go another pass with outside of the paper, literally, to find all of the information that you don't have, right? In the paper, they don't explain PPO. You need to get that information, right? And you need to get the information about reinforcement learning with human feedback. Then you get the information about like all of the models, like why the big ones have emergent ability, right? So you get like this extra information, and then you can do another pass where you go and then you chunk what you know and what you still don't know, right? These papers are very, very very rich. There's only a few people that are reading these papers that truly understand them 100%, right? So even if you understand like 80% at the end of the second pass, it's still good. Now, if you want to go like a step further and kind of be at the level where you can implement it yourself, right? Which you should not do to every paper. You should never do that to every paper, because you're gonna like you're gonna try to reproduce like the concept of the effort of many scientists that have been literally doing this for a long while, right? But if you want to go the step further, you literally go and check out the code, and then you go stepwise in the methodology to understand where stuff are. But even at this step, there might be a mistake from their side. Like there's some paper that are very super good, and still the logic that they're using is flawed, but can still work, or it has some limitation, right? So if you understand this properly, then it's not too difficult to kind of go into a paper and then read it. This one took me like honestly a solid like 4 days to go through it, and then go get the materials, and then like go and do the derivation for the stuff, look at the code from Hugging Face, to put everything together in order to fully understand what's happening. And even then, there's like 2-3 areas that are super important, and then the rest is like the whole data augmentation part. To be honest, right, it's not that relevant for your use case. If they already had the data, you can like cut this whole thing out, and then it's not there. So you have to understand also what's specific from the process to get to the result, and then what's really novel on their side. There's like 3 things that are novel in this whole thing. Let me know if that helped. But like this is the same thing in every field. And the more you read in a specific field, right, the more you realize like all of these patterns that are happening. If it's the first paper that you ever read, you're going to be super lost. But if it's like the 100th paper that you read, you already know the pattern of stuff that is happening, and you already know like the level of competence of the researcher when they're going to explain the stuff, right? Because don't forget, like it's people that are writing these, and it's multiple people. I've already seen in one team that write a paper, some people don't understand fully the whole thing, right? Like just the PI, the principal investigator, understand the full picture. The rest understand like all their bits and how they connect together. But that's kind of it.
Yes, exactly. So always look for the points or the goal of the paper. What's the paper? What paper have brought as a new information or as a new technology, or etc. etc. The other stuff you should, as Yacine mentioned, you should always go and look for the other information outside the paper, because one paper will not give you every information they have used. They're not going to give you, for example, they're not going to explain the PPO, the GRPO, etc., etc., etc. They expect you to go and look for those terms, understand them, and then come back and understand the paper more. So yeah, hint, yes, hint.
I want to ask you about the what really got me like wondering this whole session was the mathematic like equations that they wrote there. I want to know that if I want to understand them or to come to write something like that one day, how to like how to approach it. So what lessons do I need to know? What math knowledge do I need to have?
Okay, that's a very good question. Well, if you want to write novel math like this at this level, right, realize that you're never going to write it in a vacuum, right? You're not just they didn't just like wake up one morning like thought about GRPO, right? They had PPO, and most likely they already tried this whole setup with PPO and were like, yeah, it's not going to work out, right? And then they did 2 changes. The only thing that they did on PPO for the GRPO is 2 things. They changed the KL divergence, right? I think for convenience sake for the computation. And then they realized like, oh, this one has high variance because I've read this paper from this guy in 2020. Let's use his version of it, right? There was 2 versions that they could use. They decided to use the third one. They put it there. And then the second change that they did is like, do we really need a value model? can we do it without the value model? Let's try to do like some kind of form of boosting-ish, see what we get out of it. And then I did that, and it worked, right? So there's some amount of experimentation that is in there, and you base your stuff on what was existing before. However, like to have like a good first knowledge about the stuff, I always recommend this book, Mathematics for Machine Learning. This one is absolutely awesome. Let's see here. So I recommend to check out this book. It's a good gateway for all the math that you need in machine learning in general, right? Because machine learning is a very diverse field. You have like the frequentist, like statistic, Bayesian type. You have linear algebra of many sort. This book, what it does is that it like summarize all of this, explain to you where this stuff is useful, and have a lot of reference for like literally like courses, YouTube video, in order for you to get more deeper knowledge if need be, right? Don't go too crazy on the math though, right? I'm pretty sure if you ask like everybody in this research group to explain to you the GRPO algorithm, I don't think all of them will be able to walk through the whole thing. Some of them will be like, I just implemented in the code, and then I'm doing the parallelization. I'm not focused on that, right? So you don't need to be an expert in every bit of the whole paper yourself, even on the programming sense or the mathematical sense. But it's good for you to know where the surface area for math is for machine learning, what's more important, what's less important, and then latch onto this when you need to, depending on your project, right? For instance, right now, everybody is trying to figure out reinforcement learning because they know how useful it is in the post-training. If you just like rewind like 1 year or 2 years before, people were saying like reinforcement learning is garbage and it's useless. Like Yann LeCun from Meta is on stage saying like, don't use reinforcement learning, like this is wasteful, right? And now that we've seen how practical it is in this particular setup, it's like, yes, it's wasteful, but like it's useful, at least for this part. There's maybe other things that we could do that are optimal, but that thing is useful now, so we should at least understand how to use it and dig into it if we need to.